This video, I would leave it as an optional video in case you are interested. Okay. Uh, the reason why I'm putting this is so that you can get a little bit of background uh, to the Fourier transforms in the digital domain and how it relates to Fourier transforms in the analog domain. Um, it's a little bit mathematical, but the mathematics is not very tough. And my recommendation is, even though it's optional, you can just listen to it once. Um, okay, so here we go. So we know that Fourier transform of an analog signal is given by this equation. So you can write it as x omega equal to integration of minus infinity to infinity xt e to the power minus j omega t dt. Okay, so that's the equation that gives the Fourier transform of the signal that we are any analog signal. Okay, if you have sampled the signal, then we can write our time as n of t, right? Where, or let's more specifically write it as n of ts, where ts is the sampling interval. So t is only defined at the sampling instance and it's not defined at any other time. So we can write this like that. Okay. So if this is the case, then we can write x omega as, so let me just replace what was inside the integration, and thus this becomes x n ts e to the power minus j omega n ts. Okay. Now, now the issue is that what is the variable of integration here? Now, in this case, in the equation here, the variable of integration was t. But in this equation, there is no t. The variable that is changing with time is basically n, right? So instead of an integration over t, what we do is we can replace this with a summation over n. So n varies from minus infinity to infinity. So at all time instants from minus infinity to infinity, all the time instance, what we do is we can have this summation going. Okay, let's continue kind of working with this equation. So this becomes minus infinity to infinity, and let me just write it as x n. I'm leaving the ts outside, and basically xn is the nth element of the array x. So imagine all the samples are taken, and instead of being plotted in the time domain, they are now in an array, and each element has an index associated with it, and that's what xn is. Okay, and then let's write e to the power minus j, and let me just open this omega up and write 2 pi f times ts, but ts can also be written as 1 over fs, right? Because it's a sampling interval, which is the inverse of the sampling frequency. So you get f over fs n. Is that all right? So, so what is this quantity, f over fs? I'm sure you remember that this is our normalized frequency, right? So I could write this then as equal to summation of n equal to minus infinity to infinity x n e to the power minus j and 2 pi, and the normalized frequency gives me the angular frequency, so 2 pi j omega n, right? Now here what we have done is we have made this variable omega, but on the left hand side of the equation we still have the variable omega here, and we want to replace this omega with something that is associated with this capital omega. So what we can do is, so let me just take this omega off, and what we can write instead of omega is I could write omega here, okay, and that would be accurate. But instead of omega, it's customary to write e to the power minus j omega as the quantity that we write in x. And what this term does is it tells us that the spectrum itself is periodic. We have already looked at it, right? So e to the power minus j omega. Let's write it that way. Okay? Where of course omega is the normalized angular frequency. Now, what we will do in the digital domain is to still make some assumptions, to still make it more easy for us uh, to do the maths associated with this. And what we will do is we will write, we'll substitute z for e to the power j omega. And if you do that, what you get is you get x of z inverse equal to summation of n equal to minus infinity to infinity xn z to the power minus n. And this is the analysis equation for what is called the z transform, and we'll talk about it in the next video. And throughout this lecture we will be using the z transforms quite a bit to analyze uh, transformations that we do in the digital domain. But hopefully this gives you a sense of where the z transform comes from and how the normalized frequency is associated with the analog frequency, the usual analog frequency that we use for signals.